Now let's talk about HVAC system components. So in any typical HVAC system, you have four different components. One is source, where heating and cooling is produced. Two is distribution system, components that circulate the produced heating or cooling from source to zones. Three, delivery, components that deliver heating or cooling effect. And four, components that provide control over the amount of heating or cooling effect. Let's start with the source. When you talk about source in any HVAC system, you are basically talking about heat or cool, or heat and cool both. So there are four different ways to introduce heat into buildings. One is on-site combustion, meaning you are burning some fuel like gas, propane, coal, wood, and delivering that heat to your space. Number two is passing electricity through a resistance to produce heat. Number three is transferring heat from an existing source on site to where it will be more useful. And number four is capturing existing energy on site like solar energy or underground water and turning it into usable heat in the building. And when we talk about cool, there are typically three ways to introduce cool into buildings. First one is called vapor compression refrigeration. Second one is called absorption refrigeration. And the third one is called evaporative cooling. Question number 4. Which of the following heat introduction means into a building does not include the introduction of new heat energy to the building? Interesting. So you are introducing heat, but it does not include a new heat energy. Option A. Specifying a natural gas burning furnace for the heating of an office building. Option B. Installing a wood burning fireplace in the living room of a single family house. Option C. Specifying a heat recovery ventilator to be implemented into the existing HVAC system. Option D. Specifying an electrical boiler for the hot water needs of a residential unit. Please take a minute and come back to see the answer. Option C is the correct option, specifying a heat recovery ventilator to be implemented into the existing HVAC system. Because all of the options except option C suggest the introduction of previously non-existent heat energy. Burning gas, wood, or electricity means bringing new energy to the site. However, recovering the heat that's already produced and reintroducing it to the building means reusing existing heat energy, which the question was expecting from us. Let's talk about heat in general. What are the heating equipments? I would like to discuss boilers first. Boilers use either electricity or on-site combustion to heat the water to a level where it can be used for heating, or they heat the water until it evaporates and becomes steam. They can be used for heating or hot water or both. Steam can be used for heating or hot water or both. Boilers vary depending on their capacity, the type of fuel you have available on the site, or the size of the building. So there are a few different types of boilers. I'm not going to go too much into detail when explaining them, but I think you should be familiar with the names. Fire tube boilers, water tube boilers, cast iron boilers, steam boilers, modular boilers. So let's discuss what are those. So the three most common ones that I want to discuss here are fire tube, water tube, cast iron. So in fire tube, as the name implies, the hot flue gases that you receive from the combustion chamber are circulating through these tubes that are surrounded by water jackets. So as you see in the graphic here, the gas, the hot gas, is in the tube and the water is around it. So heat direction is from the tube to water. Remember, heat moves from hot to cold. So from that hot tube, the heat is gonna run through the cold water and heat that water up. And in the water tube, again, as the name implies, The tubes are now this time filled with water, and the hot flue gases are circulating around the tubes to heat the water and produce steam. So in this time, you have heat running from the gas to water again, but now water is in the tube, not around the tube. And around the tube is hot. So that's the difference. When it says fire tube, fire is inside. When it says water tube, water is inside the pipe. I think it's going to be easy to remembering that. And the cast iron boiler is essentially a cast iron tank filled with water sitting on direct fire, and that's how you heat up the water. So when your heat requirement is not too much, when it's relatively a smaller heat requirement, the fire tube boilers take less space compared to water tube boiler. So in a small project, specifying fire tube might be more ideal because it's going to take less space, and it is still going to be effective because the required capacity of the boiler is not too big. However, at higher capacity, like larger projects, the fire tube boilers get larger and heavier to meet the demand. So that's why buildings with higher demands tend to go with water tube boilers rather than fire tube boilers. Also, water tube boilers transfer heat more efficiently compared to fire tube boilers. Again, at higher capacities, they weigh significantly less than fire tube boilers. Operating water tube boilers is safer than operating fire tube boilers. At small capacities, fire tube and water tube boilers can perform similarly, but at higher capacities, water tube outperforms fire tube. And lastly, water tube boilers respond faster than fire tube boilers. Cast iron boilers are often used in residential projects and sometimes in light commercial buildings. So keep that in mind that if the question says it's a small residential project, cast iron should be good. They have low efficiency but can be modular, so that's advantageous. We are going to talk about what does modular mean in the next slides. Cast iron is a brittle material, so may not be resistant to the temperature or overheating. They are small, so good for projects with space limitations. Again, if you have a small residential project with less space for the mechanical room, this is a good option. Chemicals in the water can cause corrosion. That's an issue when it comes to cast iron. So there are also two different energy types: fossil fuel burning boilers versus electrical boilers. So if you're going to specify a fossil fuel burning boiler, you need a chimney because you need to vent that out. Air pollution control equipment is going to be needed, and ventilation or fresh air for combustion is needed. So you need a chimney. On the contrary, electric boilers do not need a chimney. Air pollution control is not required at the building, but the plant where electric energy is produced will still contribute to the pollution. So it feels like electrical boilers are more environmentally friendly on the site, yes, but you need to make sure what the plant that you receive the electricity from is using. If they are burning fossil fuels on an extreme level, your building's sustainability values might be lower than you imagined. Question number 5. Based on the breaching guidelines table for fossil fuel fired boilers below, what should be the minimum breaching diameter at pipe C if the boiler horsepower of each boiler in the section below is 150? The answer is in inches. Please carefully review the diagram and the table and come back to see the answer in a minute. So the answer is 27 inches. Let's look why. In this diagram, I see that I have 3 boilers, and the table says minimum breaching diameter in inches. I have 3 breaching spots, A, B, and C. So the question already gives them what's breaching, and it highlights the dimensions of the breaching at different spots. And when I check the table, it says number of boilers and boiler horsepower. So number of boilers is 1, 2, 3, 4, right? We have 3. My question says I have 150 horsepower. So when I look at the table, there's a value between 120 and 350. So I am in that range, so it should work for my project. And when I look at the intersection of that horsepower with 3 boilers, I see that at C, the breaching should be 27-inch minimum. So that's why the answer is 27 inches. Again, this was a confusing looking but very easy to answer question. If you have the basic skills of understanding a diagram, a drawing, and reading a table carefully without overthinking or over confusing yourself. Just look at the simple items that are given in the table and read the question carefully. It's going to take you to the right answer immediately. Question number 6. In which of the following scenarios the boiler works more efficiently and saves more fuel? A. A large single steam boiler in a cold climate that required to work at a full rate during only 10% of the winter. B. A modular boiler system where each module can work at a full rate independently as the demand increases. C. A boiler system that is oversized to make sure that heat is readily available all winter. Please take a minute, read all the options very carefully with the question, and come back to see the answer. Correct option is B, a modular system where each module can work at a full rate independently as the demand increases. Let's talk why. When a boiler works at full rate, it's the most efficient. Modular boilers are a series of independent boilers that are designed to work at full rate all the time, and when one is not enough, the rest kicks in gradually. Option B says if you had multiple modular boilers, when one is full, the other one is going to kick in, and when the second one is full at the highest capacity, then the third one is going to kick in. However, when you have a single or multiple large boilers, they work at a full rate only for a smaller period during very cold days because they are oversized to meet demand under the most extreme conditions. Because of this, during regular times, they run at partial capacity, which reduces their efficiency. The second heating equipment that I want to talk about is furnaces. Furnaces mostly use on-site combustion like gas, propane, fuel oil, or sometimes electricity to heat the air so it can be used for heating buildings. A furnace mostly uses ductwork to deliver hot air through the building. A furnace that uses on-site combustion also requires fresh outdoor air and ventilation to exhaust the flue gases, a chimney. And furnaces are mostly used in small residential buildings. In larger buildings, the job of the furnace is done by air handling unit. I'm going to talk about air handling units throughout all mechanical system videos, so it's a larger topic that we need to understand. Now let's talk about cool. And again, we are going to talk about the basics of the cooling. In this portion, I really want to explain a few things about how heat energy moves and how the molecules react to that so we can understand heating and cooling better, because it's going to help us a lot when we are discussing the refrigeration system. When heat escapes from water, the water molecules significantly slow down and water forms a solid shape and becomes ice, as you know. So heat runs from hot to cold, remember. So when you apply cold to the water, the molecules start to slow down, the heat starts to escape, which makes molecules to slow down. When they are finally really slow, that solidifies the water and makes it ice. So on the contrary, when heat is introduced to water, the water molecules now speed up, and they significantly speed up as the heat goes up. And when they speed up too much, they turn into water vapor. So the pressure inside the container that water is in now increases because the water vapor has higher pressure because molecules are moving significantly faster. This pressure is energy in the form of heat. So when you look at heat, you understand that when it escapes the body of water, molecules slow down. And when it's introduced to the body of water, molecules speed up. So heat is essentially molecules in motion, not what you feel when you touch. So when we are discussing this HVAC systems, please keep that in mind that we are talking about the movement of the molecules when we say heat. I mentioned sensible heat and latent heat when I explained the basics of sustainability and environmental topics, but I want to touch upon that again. So let's say you have a pot of water that's boiling on the stove. So you are introducing heat to the water, right? And liquid starts to become gas. We call this changing state. So latent heat is the heat that's required to change the state of water. Okay? But sensible heat is the heat you can measure with a thermometer. So look at this diagram to understand it better. So when you have a pot of water at a 0 Fahrenheit degree and you start to slowly heat it up, the temperature, as you see in this graphic, goes high until a certain point, and at exactly 212 Fahrenheit, it starts boiling. When water starts boiling, for a while, the temperature of the water does not change, but the water starts to turn into gas. So change of state starts to happen for water. Now it starts to become gas, not liquid anymore. During this change of state, latent heat increases, but temperature does not change. It's stable. So the heat energy is increasing, but the temperature remains the same. After a certain point of water boiling, we see that sensible heat starts to pick up again and temperature rises again. Another important point that we need to understand is when the container of any molecules, any sort of molecules is compressed, meaning reduced to smaller portion, it makes molecules to go faster, bounce faster, which again increase heat and pressure inside. Let's say the size of your container is 1 and you reduce it to the half, you are going to have faster molecules, increased temperature and pressure. Opposite to that, when molecules have larger containers, they bounce slower, their temperature is reduced and their pressure is less. So after this slide, I'm going to talk about refrigeration cycle. So when I say the compressor or compression, this is what you should remember, okay? In a compressed space, you are increasing the movement of the molecules. What's a refrigerant? A refrigerant is a fluid that circulates between the cooling coil and condenser coil and creates a refrigeration cycle in air conditioning systems and heat pumps. During the cycle between two ends of the air conditioning system, the refrigerant undergoes repeated change of state from a liquid to a gas and back again. This is why it's called refrigeration cycle. With the help of refrigerants, the refrigeration cycle basically takes the heat where it's not required and dumps it out where it doesn't matter. The refrigeration cycle does not produce cool, it removes heat. Okay, that's very important. Refrigeration cycle does not produce cool from nowhere. It takes the heat that exists and removes it and dumps it to the place where it doesn't matter. So now let's talk about the refrigeration cycle. Basically, refrigeration cycle has 4 main components and it takes place in 4 main stages. The first component is compressor, as you see in this image. That's how it looks like. The second component is condenser. The third component is expansion valve. And the fourth component is evaporator. So now let's talk about these 4 main stages between these 4 different components. So simply, a refrigeration cycle is the circulation of a refrigerant between these 4 components. In the first stage, the refrigerant is a gas with low pressure and low heat, and it gets into the compressor. As it exits the compressor, the low pressure gas becomes high pressure with higher temperature. Remember what happened when we compressed the gas molecules in a smaller volume? They started to speed up and they gain heat, right? So that's what happens in the first stage of our refrigeration cycle. As it exits the compressor in the second stage of the refrigeration cycle, this hot gas enters to the condenser and it loses its heat as it goes through the condenser coil. This is also known as dumping its heat to the outside. Since our refrigerant is much more warmer than the outside temperature, the heat moves from hot to cooler temperature. So we dump our excessive heat to the outside. As the refrigerant moves to the end of the condenser coil, now we have liquid refrigerant, because as it loses its temperature, the gas starts to become liquid, but the pressure doesn't change. In the third stage, our normal temperature but high pressure liquid refrigerant enters into the expansion valve. Inside the expansion valve, there is a diaphragm which allows room for refrigerant to expand. This expansion allows molecules of high pressure liquid to become low pressure and cooler. So at the end of the expansion valve stage, we have a cold, low pressure liquid entering into the evaporator coil, which brings us to the fourth and the last stage of the cycle. The low pressure, low heat liquid enters into the coil and goes down. The fans inside the evaporator blows warmer indoor air around the evaporator coil, and the room air gets cooler, because remember, heat moves from hot to cold. So the cold liquid refrigerant inside the evaporator coil removes heat from the room and absorbs the heat in its own body. As a result, the room gets cooler, but the refrigerant gets warmer and starts boiling and evaporating again. The boiling temperature of the refrigerants are typically very low, so do not think it needs as much heat as regular water needs to boil. So they have a very low boiling temperature. That's why this coil is called evaporator coil, because the refrigerant inside it starts slowly evaporating as it takes the heat from the room and absorb it in its own body. At the end of the stage 4, as the refrigerant leaves the evaporator coil, it's now low pressure warm gas, no more liquid. This low pressure warm gas is now sent into condenser again, and the cycle starts all over. So simply, refrigeration cycle is the cycle between the change of state of the refrigerant from gas to liquid. While refrigerant is changing its state from gas to liquid, in condenser coil, it dumps heat to outside, and when it turns from liquid to gas again in the evaporator coil, as the name indicates, liquid evaporates in the evaporator coil, it removes heat from the inside of the room to increase its own temperature to start evaporating. So it's a cycle between change of state of the refrigerant itself from liquid to gas. So refrigeration system and heat pumps are two different things. Refrigeration system is typically cooling only. The cycle is unidirectional. It's all about cooling indoors. When it's bidirectional, meaning the cycle is reversible, the system can both heat and cool when needed. If this cycle can be reversible, it's called a heat pump, not a refrigeration system anymore. Heat pumps can provide both heating and cooling. This is very important. Please write it down. Heat pumps can provide both heating and cooling, and if your space has both needs, you need to specify a heat pump. When we look at means of cooling, there are 3 different methods. One is vapor compression refrigeration, 2 is absorption refrigeration, and 3 is evaporative cooling. So when it comes to vapor compression refrigeration, which I'm going to call VCR, 95% of HVAC systems use vapor compression cooling. VCR requires a heat rejection system that's located outside, and VCR can produce both cooled air or chilled water. Absorption refrigeration, it's way less common than VCR. VCR is the most common. Instead of compressor, the flow process is driven by heat. Less efficient unless it uses waste heat or solar hot water as the driving heat source, and mostly used in large capacity applications that produce chilled water. Compared to VCR, it's quieter. We are going to mostly focus on vapor compression refrigeration based systems, by the way. I'm not going to talk more about absorption refrigeration because it's only a small portion, and I feel like Hcav tends to ask more questions about vapor compression refrigeration or sometimes evaporative cooling. So let's talk about evaporative cooling too. An evaporative cooler can produce the evaporative cooling effect. Please go back and watch sustainability and environment related videos to understand how evaporative cooling works better. It's very efficient, can be used to cool down both air and water. Depending on the performance can vary, but it's usually preferred in low humidity climate. In a hot humidity climate, it's not very ideal. If installed under proper conditions, it has a low global warming effect. Question number 7. An architect is working on the HVAC system of a single family home located in a climate with warm summers and cool winters. The owner prefers an easily accessible mechanical system that can provide flexibility to deliver conditioned air to different rooms on demand and be used year-round. Also, the system should not add extra loads to the roof. Which of the following option would be the best for this project? A. An air-to-air single package heat pump system. B. An air-to-air split heat pump system. C. An air-to-air split refrigeration system. Please take a minute and come back to see the answer. The correct answer is B. An air-to-air split heat pump system. Before we move to the next slide, I want to eliminate option C because only a heat pump can provide both heating and cooling, and the question says this system should be used year-round and they have warm summers and cool winters, so they will need both heating and cooling. So we eliminate option C immediately, but let's discuss split versus single package. Unitary or single package systems are one-piece units that house both inside and outside units of the heat pump. So you have the condenser and evaporative coil in the same package. They are mostly located on the rooftops. They are heavy and can get noisy, so placing them outside is better. 2 split heat pump systems. The outdoor and indoor units are totally separated. Indoor units are smaller and quieter, while outdoor units can get noisy. The main advantage is their flexibility for zoning. You can have separate units in different rooms and heat or cool as you wish at the same time. Typically, they are ductless and easy to install. So our question said we need a year-round system, so both systems meet that criteria. The owner wants an easily accessible mechanical system that can provide flexibility to deliver conditioned air to different rooms on demand. So when you have a split system, users can control each room and you can easily access to the system because in each room you have a unit, so anything goes wrong with one unit, it doesn't affect the rest of the room and you can easily access because it's in the room rather than on the rooftop. And the question says the system should not add extra loads to the roof. As I explained here, the single package heat pumps usually placed on the rooftop, so that's extra load. So the client doesn't want that. That's why we picked split heat pump systems as the best option in this question. Thanks so much for watching. Please don't forget to solve the related quiz. I will have a few more videos to cover the rest of the mechanical systems. So I wish you best of luck with your studies and your upcoming exams and hope to see you in the next video soon. Bye bye.